Hi, my name is Oded Aronson. I'm a professor and the director of the Center for Planetary Sciences here at the Weizmann Institute. The center brings together researchers from various aspects of planetary science. We have geochemistry, we have atmospheric dynamics, members of the center coming from all over the world to do research here. The center enables such collaborations by not only bringing together the relevant researchers, but also supporting them financially. And we're very proud to have this ability because it not only fosters new research here in Israel, but also enables us to have educational programs.
The center runs Israel's first graduate program in planetary science for both Israeli and international students wanting to gain expertise in research into exoplanets, paleoclimates, and the solar system.
We study other planets. Sometimes we do this by simulations in the lab, sometimes we have numerical models running on computers, and occasionally, when we're lucky, we even have spacecraft that reach these other worlds. One such spacecraft is called SpaceIL. SpaceIL is the first Israeli mission to the moon. The SpaceIL spacecraft will not only reach the moon and land on the moon, it will make measurements of the magnetic field of the moon and help reveal the origin of that magnetic field. The main goal of the SpaceIL project is to inspire and educate young people, both in Israel and throughout the world, about space, space science, and exploring space through planetary missions. I'm standing on top of the telescope observation tower on Weizmann's campus, and I wanted to take this opportunity not just to share with you the beautiful view of Weizmann's campus, but also to show you the moon, and to show you where it is that SpaceIL, the first Israeli spacecraft to the moon, where it is that we will land. We plan to land here on the Mare surfaces of the moon, and location in Mare Serenitatis, right between Apollo 15 and Apollo 17 on the boundary of the Mare.
The center also contributes to and receives data from international space missions with ESA and NASA.
For me, one of the most exciting aspects of the Center for Planetary Science is our involvement in international space missions, such as Juno and JUICE. My group studies atmospheric dynamics of planetary bodies in the solar system. We study dynamics on Earth, of course, on other terrestrial planets, and on giant planets. Giant planets have very deep atmospheres which extend deep into the interior, and we use various methods to study how deep they extend and what kind of dynamics we can find on these planets. As part of the Juno science team, we use very accurate gravity measurements that we receive from the spacecraft and use these to interpret the wind fields on the planet. Using this method, we've been able to determine the depth of Jupiter's atmosphere. The Jupiter Icy Moon Explorer, JUICE, is a European mission to the Jovian system. For JUICE, we're contributing an instrument built here in Israel that will allow us to measure very accurately the time it takes a radio beam to travel from Jupiter to Earth, and with that, we will be able to measure the properties of the atmosphere of Jupiter.
State-of-the-art facilities support research at the center, including the development of the Wiseman Fast Astronomical Survey Telescope, or WFAST, designed to observe the far reaches of our solar system.
The WFAST project is a project aimed at finding for the first time the yet unseen part of our own solar system, the Oort cloud, using two very wide field of view 57 centimeter telescopes to be located in Mitzpe Ramon, Israel, in the south of the Negev desert. Each telescope will be capable of observing thousands of stars simultaneously and to look for the minute occultations due to the passages of small rocks in our own solar system in front of background stars. The Oort cloud was never seen before. If we will find it, we will be able for the first time to detect some of the oldest bodies in our solar system, characterize them, and to have some new clues regarding the formation of our planetary system.
Experimental geochemistry is used at the center to simulate environments which either no longer exist, like early Earth and its oceans, or environments on different planets, like Mars, which are difficult to access.
We simulate those environments in the lab by controlling the temperature and the gas phase chemistry and the aqueous chemistry to try and understand the processes occurring in those environments. The climate and chemistry at a planet's surface are tightly coupled. The concentration of greenhouse gases in a planet's atmosphere controls the planet's climate and therefore its potential to host life. And we study these interactions. We study the ways in which the sources and sinks of various atmospheric compounds control the greenhouse effect on a planet and therefore its climate.
We're standing here in the cold room at the Weizmann Institute, where we simulate large-scale processes as they occur on Mars. In this chamber over here, we call this our Mars chamber. we can run experiments where we can study how water diffuses from the atmosphere through the regolith under Mars' atmospheric pressure and temperature and atmospheric composition down into the regolith to form the subsurface ice on Mars.
The Simulated Planetary Ices and Environments Laboratory contributes to my research in that it allows me to build and design my own experiments to study these fundamental processes. I chose to come to the Weizmann Institute of Science for a variety of reasons, but probably the most important factors were the large range of people that I could work with and their expertise, my access to state-of-the-art facilities, and also my ability to have autonomy in the science that I wanted to perform.
The center explores exoplanets, planets beyond our solar system, with the aim of gaining greater knowledge of their architecture and that of our own solar system.
Exoplanets are perhaps the most exciting intellectual discovery that humanity has made recently in astronomy. Here in the lab, we study specific aspects of exoplanets by looking at transit timing variations, looking at the passage of the planet in front of its host star and studying how those transits, how those occultations vary in time. This provides information on the size of the planet, but also on the masses of other planets in the system. We can study the system architecture and ask questions such as, is our own solar system unique or is it commonplace throughout the universe? What I really hope the center will do is continue to bring together researchers from throughout the world here to the Weizmann Institute to not only study the planets, but to also allow students to become expert in this discipline.